the cloud. Okay. Okay, so that's also equal to phi sub t of p. Because this position is the same as the position of the particle, which is at the time s equal to 0, sits here. Then after s seconds, it's going to be at this point. Okay, so we have so for every number t, we have a diffeomorphism. We think of f phi sub t as a diffeomorphism from S2 to itself, and it has this special property, right? So that's a family of diffeomorphisms satisfying this property. That's kind of the idea behind the notion of one parameter subgroup of the group of diffeomorphisms. Now I will give you this property that we have here can be expressed as saying that we have a homomorphism of groups. So R, this is a group of real numbers under addition, and so this phi, right? Now I do not fix t, so I can think of this family altogether for all t as a homomorphism from the group of real numbers to the group of diffeomorphisms, right, of my manifold, which is in this case S2, right? So t goes to phi sub t, and the saying that this map is a group homomorphism, well, what is the group structure on R? It's just addition. And what is the group structure here? It's composition, right? Here the operation is commutative. Here is highly non-commutative because composition of maps is non-commutative. Nevertheless, so this property tells us that saying that it's homomorphism means that homomorphism of groups is equivalent to saying that phi sub t plus s is equal to the composition of phi sub t and phi sub s. And of course, t and s can be interchanged here. So this formula is also a corollary of this one. So this is for all t and s in R. So that's kind of what one parameter group of diffeomorphism informally is. And now I want to give a formal definition. So when I give a formal definition, what you should kind of pay attention, well, you should I want to draw your attention that okay, so maybe first I'll give you a definition, then I comment on this. So formal definition is the following. One parameter group of diffeomorphisms is a map, a smooth map from which I will call also phi from, I'm sorry for using notation a little bit. So that's going to be now a map from M times R to M. Yeah, and my M is a smooth manifold. Smooth manifold, which I'm going to fix for the rest of this talk, this lecture. So such that the following holds. So I'm going to write phi sub t of p for phi of p comma t, such that, well, the following two properties. So phi sub 0 of p is p. Okay, so I can think of phi sub t again, right? If I fix t and vary p, then I can think of this as a map from M to itself. And so my first property is that phi 0 is the identity map. That's this property. And the second property is that phi of s phi of s plus t is the composition. So, well, the remark that you see, we have a smooth map from M times R to itself. This is my phi. Not to itself, just to M, sorry. And phi sub t is obtained by restricting this map to closet subset, which is a submanifold, which is just M times t. And I need to erase this. Okay, this is M times 1 point. It sits here. So the composition is what we call phi sub t, and because phi is smooth, and this map is also smooth, right? I can identify it with M. The composition is also smooth, so phi sub t is smooth. So we have M, we have phi sub t, which is a smooth map from M to itself, and we also have map phi sub minus t, and the composition of these two maps is by 2 is phi of 0, which is the identity. So that means that phi sub minus t composed with phi sub t, it's also equal to the composition in the other direction, phi sub t composed with phi of minus t, and this is identity. So that means that phi sub t is a diffeomorphism, right? It's an invert, so it's a smooth map such that it has an inverse map, which is also smooth. And so this property in particular, so for every t we have a diffeomorphism. So let's return to this picture. So let's see what it adds, this formal definition, why it's different from what we have here. So the difference, so we definitely have this property, and phi 0 here, it's a homomorphism, so it takes 0 to the identity, right? So what this formal definition adds is, well, it expresses the idea that this map itself is somehow smooth, that phi sub t varies smoothly as I vary t, right? It's not that for one t I have one diffeomorphism, and for very close t I have completely different. So, and this is expressed by saying that this function in kind of in two variables is smooth, right? So it requires smoothness in T as well. That's the main point of this definition, compared to what we had before. So very good. Now I want to link this notion of one parameter group of diffeomorphisms with vector fields. Right? That's an important construction. So suppose I have phi sub t as above, and I also have a smooth function. Then, well, what I can do, I can compose these two. I can take, I can first, so I have M, I have phi sub t, and I have F. So this is mapped to real numbers. This is F. So I can take the composition F of phi sub t. I can pick some point P. And think of this as so it's actually a function in two variables, right? So it's function in T and it's also a function in P, right? So this is by very definition, it's a smooth map from M times R to R. So very good. So I can, if you wish, I can the smoothness of this map comes from the smoothness of this phi. Now, okay, so let's think first of this as a function in T, and let's take its derivative with respect to T. So I may fix P and just consider this as a function in one variable. Yes. So this is still a function in T. Well, and if you have vary P, it's going to be also a function in P. But let's take its value when T equals 0. Right? So so what is now when I specify T equal to 0? This is just a function in P. And this is a smooth function. If I have a function on M times R, I differentiate it with respect to T. I again get a function, smooth function on M times R. I evaluate it at T equals 0. I get a smooth function on M. And now the Leibniz formula, the product rule, tells me that this operation that sends a function f to this new function is a derivation, right? So let's give a name to this. Let's denote this. This is notation theta of f. Then what we have is that theta of f times g is equal to f theta of g plus plus theta of f times g. So why this is true? Just because, well, first of all, this substitution of phi definitely takes product of functions to product of functions. And so this derivative with respect to t satisfies the Leibniz form. So you immediately get this for free. So you also have to remember, right? So let me do this computation for you. It's very simple. So what I need to compute is d over dt of well, I have two functions, f of phi t of p, g of phi t of p, and I must take derivative and then evaluate it at t equals 0. So, and just by the usual Leibniz formula, that's the same. So you differentiate product of two functions. So you plug the first function. So the result is going to be here. Well, you differentiate the first factor, which is this. At t equals 0. And you multiply the second factor by the value of the second factor when t is 0. But because phi 0 of p is p itself, you just multiply it by g of p, right? And then you get the same expression in the opposite direction. Let me just put dots here because it's clear. You just reverse the order. And then you'll get this formula. So this formula tells me that this operation that takes f to this derivative is a derivation, which means that theta is a vector field. Get a vector field. Very good. So let's just do a small exercise on manipulating this, writing down vector fields in coordinates. So let's consider, let's take for M R2, and I will give you a one-parameter family of diffeomorphisms. So my phi sub t, it's going to be mapped from R2 to itself, and it's going to be a linear map. And I define it by the matrix. So the matrix will be cosine t, sine t, minus sine t, cosine t. So what is this map geometrically? This metric defines it represents the rotation through angle t, counterclockwise rotation. Okay, so and clearly, so let me write down this where x comma y goes. It's going to be point. Let's see here. So x cosine t minus y sine t, and now the second coordinate is going to be x sine t plus y cosine t. So let's compute the corresponding vector field. What does it mean? So to compute, well, any vector field on R2 can be expressed as f times a function times d over dx plus another function times d over dy. Yes. And so how to find f and g? Well, our definition of the vector field corresponding to a one-parameter family of diffeomorphisms, right? It's the fact that it's one-parameter family of diffeomorphism just follows from the fact that if you consider rotation through angle t and then through angle s, it's the same as rotation through angle t plus s, clear. Or it corresponds to the usual sine and cosine rule for formulas for sine, sum of two angles and cosines. So how to find the f and g? So theta were defined as by how it acts on, how it as a derivation, right? We know how to apply theta to a function. And we want to express this derivation in this form. So definitely this function f is theta of x, right? So I think of x now as a coordinate on R2, which is a function, right? And if I differentiate this function x along a vector field given by this formula, f d over dx plus g over dy, this term, well, its derivative with respect to y is 0, so what I get is f. So now let's plug here. So this we know how to compute. We have to take function x, compose it, right, with phi sub t, and then take d over dt at point t equals 0. So what is this composition? That's just this first coordinate here. So it's d over dt of x cosine t minus y sine t. And we are computing the derivative of this at t equals 0. And when we do this, well, what you'll get is this term goes away, so you get just minus y. And similarly, applying computing theta of y, you find that g is equal to x, so therefore theta is equal to minus y d over dx plus x d over dy. So so let me draw a picture. So if you look at say so to draw the picture, it's useful. Let's consider, so we have one parameter family of diffeomorphisms. So I pick a point P and I start applying these elements of this group, phi sub t of it. And because we have geometric interpretation of phi sub t, it's rotation, so the trajectory of point P as time goes is going to be a circle, right? Passing centered at the origin, passing through point P. So the kind of the geometric picture that you should have in mind when you so that's kind of, this was an algebraic definition. I could also give a kind of more geometric definition. Well, so let's just take a point P and let's start and very small t. So let's consider a path on my manifold, which is in my case R2, which takes a point T to phi sub T of P. So this is the path. So every path determines starting at point P determines a tangent vector. That was a geometric definition of tangent vectors, right? We had algebraic definition, derivations, and we have also geometric interpretation. So look at this path. Well, and this path determines tangent vector. So this is my vector field. So my vector field at point P, the tangent vector at every point P, my vector field is tangent to this circle, right? Which is clear. So if you the coordinate of this vector is x comma y, and the coordinates of this vector is minus y x. So the dot product is 0. And another property of this vector field is that these two vectors have the same length. Okay, so the velocity of a particle moving on this vector field is equal to the distance of my particle from the origin. Okay, so very good. That's the geometric meaning of the construction. Now, this is all very good, but now I want to reverse this construction. This is a more delicate question. So starting with a vector field, I want to construct a one-parameter group of diffeomorphisms. And kind of the possibility of this construction comes from this intuition with particle moving with the wind. So reverse construction. This construction. So okay, so the construction that I just explained involves taking derivatives. The inverse construction involves integration, or more precisely, solving differential equations. So the starting point is the notion of an integral curve for a vector field. So suppose I have manifold M, vector field theta, and a point on my manifold. So an integral curve through P for theta through P is a smooth map it's a map from an interval to M. I will call this map gamma. And so A and B here, B is an interval in R, and I assume that it contains 0. And the properties are the following. Well, first of all, gamma of 0 is P. So it passes through point P when T is 0. And the second property is, well, I will first write down a formula for you. So I have a map of smooth manifold, so I can take its differential, right? Differential of gamma at point T. So what is a differential? Differential is a map from the tangent space to this manifold to the tangent space at this manifold, for this manifold. And so this tangent space, well, this is an open subset of R, so the tangent bundle is trivial. I have vector d over dt, which trivializes, which is, well, I have a basis in every tangent space. So let's take this differential and let's apply it to just d over dt. So again, so dt gamma, I think of this as a map from the tangent space at point T to AB to tangent space at point gamma of T to M, and here I have tangent vector d over dt, and I plug it here. So what I should get is a tangent vector at M, and I want this to be theta evaluated. Well, I can only evaluate it at point gamma of t. So two properties. That's called the initial condition, and that's the differential equation. So, well, here is a more geometric way of expressing this. So you have a vector field, and you have a point P. So, and the integral curve is a parameterized path, right? Which is at every point, it's the tangent to this path, the tangent vector corresponding to this path. Remember that tangent vectors correspond to equivalence classes of paths. In particular, if I have a path passing through a point, then it determines a tangent vector at this point. So my requirement is that this should be a path such that the tangent vector at every point corresponding to this path is my theta. So that's the notion of integral curve. So let me maybe rewrite these two conditions in coordinates to make the relation with ordinary differential equations clear. So let's take for M Rn. Well, then any vector field can be written as F1 d over dx1 plus Fn d over dxn. And so what does it mean? So suppose I have a point, so P. So what does it mean? What is an integral curve? So an integral curve is a map from some interval containing 0 to Rn. Well, you have the condition that gamma of 0 is p. Okay, so this is a vector-valued function. Well, coordinates of this function. Well, it's a smooth vector-valued function. And it has a property that if you take the derivative of this function at point t, then so this is a vector-valued function. So the derivative is also going to be a vector-valued function. You just differentiate coordinates, and this vector-valued function is just f1 of gamma of t f n gamma of t. So these are the two conditions. This is called an ordinary differential equation. It's in fact, any ordinary differential equation can be written in this form. It's a very general differential equation. Ordinary means that it's an equation for function in one variable. It's a vector-valued function. You can think of this also as a system of differential equation, right? I'm going to use the two main theorems in ordinary differential equations: the existence, uniqueness, the existence and uniqueness of solutions, local solutions. And also I'm going to use another theorem which tells me that the solution of an ordinary differential equation depends smoothly on the initial condition. That's the initial condition. So here is how I'm going to apply it. So theorem, which is, in fact, as we're going to see, just a reformulation of the classical theorem, main theorem in ordinary differential equation. So given theta and p, there exists a unique maximal integral curve. Through P. So what does it mean, maximum? So we say that one integral curve is we have so if I have two curves, say A and B, and gamma 2, which is like this, we say that gamma 2 is greater or equal than gamma 1 if A2, B2 contains A1, B1, and gamma 2 restricted to A1, B1 is gamma 1. Okay, so you have a point, and you so you start drawing. You have a vector field. You start drawing integral curve, but it is possible that this curve cannot be extended outside of some finite interval. Let me give you an example. Let's consider for m just open interval.
Excuse me, we can't hear you. Okay, so it seems that I have some problems with Wi-Fi connection with HEC network. So I'm using my phone now as a router. I'm not sure how fast it will be, so but we'll try. Okay, so I will start again recording. Try again. Again. Okay. Can you hear me now? Yes.
Very good. So, I want to give an example of a very stupid example, but still of a maximal integral curve. I take for m interval from -1 to 1, I take p equals 0, and then theta is going to be d over dt, d over dx. Yeah, not to confuse it. Then it's clear that after time, if you start at this point, which is the origin, after time 1, t equal 1, you move outside of this interval. So the integral curve, maximal integral curve here is
going to be curve is just a map from -1 to 1 to my m, and this is gamma, and gamma of t is just x, the identity map. Okay, so it need not be defined an integral curve, need not be even a maximal integral curve with respect to the order relation that I introduced, right? So it's a partial order on the set of all integral curves. A priori, it's a partial order. So it need not be defined on the entire real line, as this example shows. And even if my manifold M is kind of big, like real numbers, you can find an example of a vector field on R such that maximal integral curve is still defined only on a finite interval. Well, how to do this? Just from point of view of geometric of differential geometry, R cannot be distinguished from interval, right? You can find the diffeomorphism from between R and this interval. So all intrinsically defined objects like vector fields, integral curves, right? They correspond, vector fields on R correspond to vector fields on this interval. So we should take this this vector field on the interval, apply diffeomorphism, and get a vector field on R, the same properties. Okay, so it doesn't hold for R as well. So the maximal integral curves defined only can be defined only on, well, at least in some cases, maximal integral curves are defined on the finite interval. Okay, so let's return to the proof of the theorem. So I recall that the theorem asserts that for every smooth manifold M, for every vector field, and for every...
Excuse me?
Yes?
On the previous slide, so gamma of t equals x.
Yes.
You say that there is no maximal interval, no maximal integral curve.
No, there is always a maximal integral curve. That was the assertion of the theorem. I'm saying that in contrast with the intuition that we have with a particle moving with wind, right? So imagine again, so picture for yourself a vector field with wind velocity, then it seems like that so you can trace your particle for arbitrary large t, right? It never stops. It always goes somehow around the Earth. But as we are going to see, the key property of the sphere that is used here is compactness. When my manifold M is compact, all integral curves are defined for all t, right? And when my manifold is not compact, like interval from -1 to 1, maximal integral curve, well, it always exists according to the theorem that I'm going to explain, right? Whose proof I'm going to explain, is defined only on, could be defined, well, in some cases can be defined only on the finite. So, so for example, here it cannot be extended beyond this interval. So I have to repeat the statement because so the interruption caused that all my notes are lost, but not video recordings unfortunately. So this part will be recovered. So theorem asserts that for every vector field theta and p in M, there exists a unique maximal curve. Okay, so let's prove this. The hard work is again the main theorem in ordinary differential equations for n, and I'm going to use it. Sort of proof, again, it's in quotation marks because I'm not going to do the difficult part. Applying the main theorem in ordinary differential equations to local charts. So pick a point, P, look at an open chart, identifying neighborhood of this point with Rn. So then a vector field is just given by n functions on Rn. The equation that a vector valued function gamma is an integral curve is an ordinary differential equation. We can construct integral curves locally. So integral curve exists. By this, I mean that there exists some interval, maybe very small, and a path gamma defined on this interval, which is tangent to my vector field and passing through point P, right? Because this statement has nothing to do with global properties of M. You just can replace here M by Rn. And then, as I explained in my example, the condition on gamma is expressed by an ordinary differential equation. So then if I have two integral curves, so I still want to prove that there exists a maximal integral curve, right? So how to show this? What I have to show is that if I have two integral curves, say B1 to M, and another integral curve and I assume that 0 sits both here and here, then two curves, integral curves, then again by if you consider the set of, if you consider the intersection of these intervals. So on the intersection, you sort of have two maps, gamma 1 and gamma 2 to M, and you can look at the points where gamma 1 of t is equal to gamma 2 of t. Let's call this this set U. So, and I claim that U is open and it's also closed and P is in U. All right. So it's open and closed in intersection of two intervals. So the fact that it's closed is obvious because these are two continuous functions. So the set of points where they are equal is definitely closed. So P is in U because our two integral curves are, well, we consider integral curves through P. So when T is 0, oh, sorry, this must be 0, not P. When T is 0, gamma 1 of 0 is equal to gamma 2 of 0 is equal to P. The non-trivial statement is that it's open, right? So what does it mean? It means that, so if you have two integral curves, and there is some point t equal to t0 where the curve meets, then in fact they coincide at least in some neighborhood of this point. Okay, so and this is this follows. This is again a local statement, right? Because I want to show that they coincide in a neighborhood. And for this, I can replace M by Rn, and then my assertion is the uniqueness property of solutions to ordinary differential equations. So for every initial condition, there exists only one solution in the neighborhood. So so this shows openness. In fact, integral curves cannot intersect one another. So it's open, closed, non-empty in this interval, which implies that U is the intersection. Okay. So and this is enough. In particular, it shows that there exists a maximal integral curve. Because if you have two curves defined on one is on this interval, another on this interval, then there exists a curve, integral curve, which is defined on the union of these two intervals, right? Because you can the two integral curves agree on the intersection, so you can extend it to the union. Okay, so you can consider all integral curves, all intervals, corresponding intervals, take the union, and then on this union you're going to have an integral, and the uniqueness is also follows. Very good. So now, so I'm going. I want to go back to notion of one-parameter subgroups of diffeomorphisms. And well, as you may see, the situation here is not as good as you may hope for. So a vector field, so we already know that one parameter group of diffeomorphisms defines a vector field. And I want an inverse construction. This does not work in general. So here is, however, a theorem which gives a kind of a partial inverse construction. So, so the subset consisting of maybe before I state the theorem, sorry, let me erase it. So I want to give
explain what we are going to do informally, right? So, so you have a vector field, and I want to produce a one-parameter family of diffeomorphisms. So what I'm going to do, I pick a point, this point, P, and I want to define phi sub t of P. Yes. So how to do this? Well, again, using this analogy, this particle moving with wind, you should look at the integral curve passing through this point P and define phi sub t of P to be simply gamma of t, where this is an integral curve through P. So the problem here, however, is that this is not defined for all t. So the theorem sort of asserts that, well, summarizes what can be done. So the subset U of M times R, where okay, so this is subset of pairs P comma T where phi sub T of P, which is given by this formula. This is integral curve through P is defined. Okay, so again, so what is this subset? So I look at all pairs P comma T such that if I look at the integral curve, maximal integral curve through point P, it's defined at this time, T. I hope that this makes sense. So, and they should also write that this is maximal. So is the first assertion is that this subset is open. The second assertion is that the map phi from U to M, which takes point P comma T to phi sub T of P, is smooth. The third assertion is that you have the basic property of one parameter group of diffeomorphisms, phi sub T composed with phi sub S is equal to phi sub T plus S whenever T, well, both sides are defined. When defined. They're defined again only on U. And last property is that if M is compact, M is compact, then U is M times R. So in this case, you actually get
and one parameter group of diffeomorphisms. So it's defined for situation as nice as you can hope for. So, well, property 1 and 2 are local statements, and they are gain corollaries of a theorem in ordinary differential equations, which is called smooth dependence, corollaries of smooth dependence on initial condition in OD. Okay, so let me explain how you get 3. Well, that's this is easy because so we want to compare phi of s plus t of p and say phi of t applied to phi of s of p. So let's think of this as functions in t. So then both are integral curves for theta through point when t is 0, they both equal to phi sub s of p, right? So that means that they coincide because we have uniqueness of integral curves passing through a given point. Yes, if two integral curves intersect one the other, then they actually coincide, and this is what happens here. And lastly, we have property 4, so M is compact, and we want to show that U is everything. Okay, so we have, let's draw a picture. So we have M, and we have R, and we have an open subset U in the product. U is M open subset in M times R. And this open subset definitely contains M times 0, right? Because at least, yeah, so on M times 0, my phi is the identity. So you have topological space M times R, and you have an open neighborhood of this vertical of this copy of M sitting in the product. So something like this. This is my U. But now using compactness, of M. Any open neighborhood
any open subset which contains this m times 0 contains kind of a cylinder, which is m times interval. Minus epsilon, epsilon. Let's call it I. So this is what fails if M is not compact. You can imagine hyperbola, right? Something like, sorry, better picture. So you can imagine something that, say, sits to the in between these two pieces of parts of the hyperbola. So clearly it doesn't contain any cylinder. So how you see this? Well, every point has a, by definition of an open set, every point of M, right? Every point here contains a small cylinder sitting inside U. That is because cylinders form a base for the topology. So you can cover your M by cylinders of this type. And because M is compact, you can pick a finite subcover. So you just take for epsilon the least, the smallest width of the cylinders. Okay, so at least we know that our phi is defined, phi sub t is defined for t here. But now it's almost immediate. Okay, have some. Okay. Seems that I again have some problems with internet connection. We'll see what will happen. So anyway, so I'll have to I will finish the proof and then we'll make a short break. So so our again our U contains m times this interval, and now define. I'm going to show that in fact phi, which is defined already here, can be extended to the entire m times r. So phi t of any point P as follows. So simply I'll take phi t over n composed with phi t over n, take composition n times and apply it to P. So here t over n is in I. So my goal is to construct, so what we want is to show that this phi, which is defined already on U, can be extended to the map from m times r to m. And here is how I'm going to do this. I pick any number t and any point P on my manifold, and I pick n so large that t over n belongs to this small interval where phi is already defined. And then I am going to use well, this formula as a definition. Why it makes sense? Because if t and t over n are both in I, then this formula holds true for phi which is already defined here, right? And that's a corollary of of this assertion that we yeah, it's a corollary of this formula. So so let's motivate this definition. Now I claim that for any t and s, phi sub t plus s of p is going to be phi of t composed with phi of s. Well, why this is true? So that's true because this is definitely true for when t and s I and I. So it's true for very small t and s. And also we have this formula. Remember that so this additivity property, this formula here implies in particular that all these diffeomorphisms commute. So in particular, when n is a very big number, phi sub t over n commutes with phi sub s over n. So therefore, this property is a corollary of the fact that it holds on m times n. So this implies that actually u, which is defined as maximal, is well, maybe I'll write it as follows. So this follows that phi t of p, which is now a map from R to M, is an integral curve. Integral curve through P, right? Because it's it passes through point P. It's defined for all R, for all T, and it's definitely tangent to the vector field theta. So it means that U is actually M times R. All integral curves are infinite. Okay, so this completes the proof of the theorem. So I want to summarize the last part of it by saying that, so this gives in the case when M is compact, if M is compact, then there is a one-to-one correspondence between vector fields and one parameter subgroups, groups of diffeomorphisms. Yes. So, because if M is compact, the last theorem gives me, starting with the vector field, it produces really this homomorphism from R to the group of diffeomorphisms, phi sub t, which is defined for all t. Very good. So let's have a 20 minutes break. So we'll resume precisely in 20 minutes, which is going to be 18:08. then a vector field gives rise to one-parameter group of diffeomorphisms. So you have two one-parameter group of diffeomorphisms, and you can ask whether diffeomorphisms sitting in these two different groups mutually commute with each other. So the Lie bracket measures how far this diffeomorphism from commuting to each other. There is a precise mathematical relation. Well, today I will explain one way of phrasing it. So let's start with let's consider a manifold M, and let's suppose that we have a diffeomorphism. Then f acts on functions. For if you have a smooth function, you can compose capital F with little f, so you get a f composed with f, and that's again a smooth function. So another way of saying it is that diff viewed as a group acts on Cm. This C infinity M is a representation of this group. If you really want this operation to be the formula that I give here defines actually anti-representation. If you want kind of a true representation, you should put capital F inverse here. Okay. So then anti-representation means that it takes product to the composition, but in the different order. So for the purpose for my purposes, it's convenient for me to use this definition. So let's apply this to assume that my f comes is a member of one parameter of one parameter group of diffeomorphisms generated by a vector field. So what does it mean? It means that you have it means that precisely that this collection phi sub t defines a map from an open neighborhood of m, 0 sitting n times r, which is additive when it makes sense with respect to t, takes sum to the composition. That's the precise meaning is stated in one of the theorems that we proved earlier. In the case when M is compact, I can think of f sub t just as a really one parameter family of diffeomorphisms. So then we can take f composed with phi sub t of p. So we get actually a family of functions parameterized by t. And as usual, when we have a family, we can take its, let me not, I do not need this p here. So let's consider this as a family of functions. Well, a function defined on m times r, or open subset of that. Okay, so, and in any case, I can definitely take this for every p, this is well defined for small t. So in any case, I can take its derivative, even if M is not compact, I can take the derivative when t equals 0. And this gives me this gives me, this is again a function. And I claim that this is nothing else but derivative of my function f along vector field theta. So why this is the case, I'll draw a picture. So what is written here? So what do you suppose you want to compute this function at point P? What you're supposed to do? You are supposed to take f of phi sub t of P. So what is phi sub t of P? This is integral curve. So it's a curve tangent to vector field theta. So you take function f, you restrict it to this integral curve, and you take derivative when t equal to 0. What you get is precisely the directional derivative of f along vector field, along tangent vector theta. Okay, so this is true by definition. Good. Now, diffeomorphisms act not only on functions. They act, this group acts on anything which is intrinsically defined in terms of smooth structure on M. Why is that? What is a diffeomorphism? So if you have a diffeomorphism f from M to M, you can think of, you can put, if you wish, give a new name to this M, call it M prime. And you can think of this as just a way of renaming elements of M. So a function on this manifold, so diffeomorphism is a bijection, a smooth bijection, such that its inverse is also smooth. So it identifies everything which is intrinsically defined on this manifold. So if you have a function here, it gives you a function here. So you just take the composition. Similarly, if you have a vector field on this manifold, diffeomorphism should produce a vector field here. Let's see how it works. So so slogan here that f diffeomorphism of M acts, the group acts on vector fields. Let's see how. If I have such f, then I can look at its derivative, say at point P. Derivative of f, which is a map from the tangent space to point P. By the way, I think the Russian name for this object is differential. And I'm used to actually call it differential, the map on the tangent spaces. But I see some the English tradition, not probably the American English tradition, is to call it derivative. Okay, so that's I stick to this. So TP of M goes to T f of P M. So because f has inverse, this map also has inverse. It's given by a differential of the inverse map. So this is, in particular, this is a isomorphism of vector spaces. So now, so that means that if I have a vector field, just a vector, say C f of P. Here, I can look at corresponding vector here. I will call it tilt, Xi tilt of P. So a diffeomorphism gives me a identification between the tangent spaces, these two tangent spaces, and in particular, if I now let P vary, then I can use this to produce, starting with a vector field Xi, which is now defined for all tangent. Well, that means that for all points, I have a vector in the corresponding tangent space. I can use this to produce a new vector field. So, given a vector field C, define a new vector field which I will call F rho star of Xi as follows. So it's so its value at so any point P. This is a tangent vector, and I can apply differential of F at point P, and I require this to be Xi computed as F at F of P. This makes sense. So let's look again at this picture. So I have this vector, and now I look at its per-image, and I declare this to be F rho star Xi computed point P. That's for this formula. So, okay. So, this defines an action. Again, it takes product, it defines anti-representation of the group of diffeomorphisms on the vector space of vector fields, meaning that it takes composition to composition in the opposite direction. If you want a true action, you should put inverse here. You should apply this construction to F inverse. Compose it with anti-involution of the group of diffeomorphisms, which takes a diffeomorphism F to its inverse. Okay, so this is one way of thinking about action of diffeomorphism on vector fields. Another way of thinking is by how you may so another point of view on vector fields is that a vector field is a derivation. How, suppose you have a vector field theta, so suppose you have a vector field Xi, and so let's look at this new vector field as a derivation. And it's immediate to see that this new vector field has a property that if you apply it to a function, which is F composed with F, you get, you take the original derivation, apply it to F, you get a function, and you compose it with F. Okay? So let me rewrite this formula a little bit. So what is, suppose you want to compute this derivation, apply to F. What you're supposed to do? You are supposed to, this formula tells you how you apply it to F composed with F. So first thing that you want to do, you want to take F, and then you want to compose it with F inverse, right? So this gives you a new function, and you can apply C derivation to this new function. This gives you another function, and you can compose it with F. That's the form. This is the code. So yet, well, another way of thinking about this formula is the following, that derivations, vector fields, is the same as derivations. And this is a subspace of the vector space of R linear endomorphisms of vector space C infinity M, right? Well, what is a derivation? In particular, it's a linear map from C infinity M to itself. Now, we already discussed that C infinity M is a representation of a group of diffeomorphisms. That's the very basic construction that we started with. So imagine that you have abstractly any group acting on a vector space. Then it also acts on the space of endomorphism of this vector space. Well, there are many actually actions. The action that we are interested in is the adjoint action. So if you have a any diffeomorphism defines endomorphism of the space of C infinity function, and you can now consider action of endomorphisms. Well, you can automorphism of a vector space acts on the vector space of all endomorphism of this vector space by conjugation, and that's the action that we consider. Okay, it happens that it takes derivation to derivation. Does it make sense? Okay. So now let's now apply this construction to the case when my F is one parameter, is a member of one parameter family of diffeomorphisms generated by that. Okay, then define the notion of Lie derivative of a vector field C along theta as follows. So we take phi sub t, we apply it to our C, we get a new vector field which depends on t, right? So you can think of this as a function in t with values in vector fields. And now I take its derivative when t is 0. So now, so this is again a vector field, right? Because you have a function in t with values in vector fields. You differentiate this function, and you get you plug t equals 0. You again get a vector field. This vector. So later in this course, we will study differential forms, metrics, or other kind of tensors. So these objects, well, they are, again, sections of certain vector bundles, intrinsically defined. They depend only on smooth structures. Mathematical meaning of this is that you have action of diffeomorphisms on these objects, on differential forms, on metrics, and so on, polyvector fields. And whenever you have a vector space on which you have action of the group of diffeomorphisms, you can use this construction to define action of vector fields on this vector space. So what we use here, so we start with an object on which diffeomorphisms act. We apply one parameter group of diffeomorphism corresponding to Xi, and then we differentiate with respect to T and plug T equals 0. So, well, there is a subtlety here, which is related to the fact that unless M is compact, phi sub T is not defined for all T. But again, around for any point P on a manifold, this phi sub T is defined for small t, and because I compute derivative only when T is 0, that makes sense for any vector field. This is a very important construction. However, in this case, you don't need to, in order to compute Lie derivative of theta, of Xi with respect to theta, you don't need to go to complicated procedure of solving ordinary differential equations, because you first integrate something when you produce, starting with a theta, one parameter family of diffeomorphisms, but then you differentiate. So these two procedures cancel each other, and so the result may be a proposition which is very simple, is that Lie derivative of theta of Xi with respect to theta is a commutator of Xi and theta, of theta and Xi. Okay, so let's prove it. So let's just compute by definition. So okay, so I want to see how this vector field acts on a function. What I'm supposed to do? I'm supposed to take phi sub T rho star. This is the formula of Xi, and then I'm supposed to take its derivative d over dt and substitute here t equals 0. Okay, so now and then I want to apply it to a function f. So definitely we can first apply it to a function f. So we apply this vector field, which depends on t, to a function f. We get now a function on m times r, right, which is defined actually for small t only. It's defined on this open set u in m times r. And then we differentiate this function in t and plug t equals 0. So let's look at this expression. So this is let's use the formula that we have here, right? It expresses how diffeomorphism acts on vector fields regarded as derivation. This is conjugation with diffeomorphism. So, and I will write it here, d over dt.
and then I have to take my C. I have to apply it to function f composed with phi t inverse. And then, so this is again a function. They compose it with phi sub t. This is still a function. I differentiate it and plug t equals 0. So this guy can be computed by the Leibniz formula. So you first differentiate this function with respect to t. If you differentiate this function with respect to t, you get, well, you can use the chain rule. So this is just, it's going to be minus comes because here I have, this is phi inverse of t. If you wish, I could rewrite it as phi minus t, right? But this is a one parameter group of diffeomorphisms. So this is equal to minus c applied to theta of f, right? So that's because if you take f composed with phi sub t and then differentiate it with respect to t and plug t equals 0, you get precisely this. That's the formula that we had somewhere here, right? And again, minus sign here comes from the fact that you have here. And then you have plus theta from now you differentiate this c applied to f. And this is precisely the commutator of theta and c applied to f. Very good. So this proves the claim. Let me finish this lecture by stating a definition. Well, so definition of a Lie group. So Lie groups are a very important source of examples in differential geometry, and not only in differential geometry. And they will kind of have many, we'll come back to this subject many times along this course. So the purpose of this kind of, I just want to illustrate several concepts by looking at simplest Lie groups. So what is a Lie group? A Lie group is a group which is also a smooth manifold. So a Lie group is a group G plus a smooth structure on the set, on the underlying set, such that, so first of all, I have just a plain group, plus I have a topology on the underlying set, plus I have a smooth structure. Such that these two structures, algebraic and analytic, are compatible in the most obvious way. So first of all, you have multiplication map. M of G1, G2 is G1, G2. And secondly, you have the map I from G to itself, which takes point G to G inverse. These two maps are smooth. So the product and inverse are smooth functions. So that's most natural definition you can make, compatibility definition. Okay, that's it. So what are examples of Lie groups? No, let's start with let's consider one example is a group of matrices, GLN, invertible matrices. So this is a group with respect to multiplication, but it's also an open subset of the space of all matrices. So this is, you can identify all square matrices with Rn squared. So this is a vector space. This is just Euclidean space, so it has a smooth structure. And this is, if you use it, so in particular it has topology, and with respect to this topology, this is an open subset. So you can use smooth structure here. A smooth structure on a set, on a topological space, defines a smooth structure on any open subset, right? You can use the same, charts. Defines a smooth structure. So basically, here you have global coordinates, right? You have every matrix is, you can write it as you can look at entries of your matrix. This A, I, J define functions. So, and altogether identify the set with open subset of Rn squared. So this is a global chart. The smooth structure is just given by declaring that this map is diffeomorphous. So the product map, it's given by polynomial functions in terms of this coordinate, so it's definitely smooth. The inverse map, you can to check that it's smooth, you can use the adjunction formula if you want to compute inverse of a matrix Aij. Then it's equal to the adjoint matrix multiplied by the determinant Aij inverse. So this, in terms of this coordinates, the adjoint matrix is also given this map from GL to GL, which takes a matrix to the adjoint matrix, is also given by polynomials. So it's definitely smooth. The determinant itself is a map from GLNR to smooth. And it's also a non-vanishing smooth function. If you have a smooth non-vanishing function, its inverse is also smooth. So this kind of is a hint, at least, that this is a Lie group, right? So it makes it, I leave some details, and it's part of the homework assignment that you're supposed to bring up, that to check that these two properties hold. So this is the most basic example of a Lie group, most important also. So so what else can you do? You can take various subgroups here.
So for example, you can take, say, you can also take matrices with complex coefficients. This is a, you can think of this as a subspace of complex vector space. But complex vector space is also a real vector space of whose dimension is twice n squared. So it also has a smooth structure, and this is an open subset, so it requires a smooth structure. It requires even more. It's a complex analytic manifold, but in particular, it's real. So this is another example of a Lie group, and you can take various subgroups. For example, here you can take the orthogonal group UN. Right? So the orthogonal group is consists of all matrices that preserve the Hermitian form here. So that means that it's A in GLN C that consists of all matrices satisfying the equation that A conjugate times A T transpose is equal to the identity. So I claim that this is a submanifold here. So not any subset is a submanifold. So let's try to check this. Let's try to. So I want to define a smooth structure on UN by declaring that a function on UN is smooth. Continuous function on UN is smooth if and only if it's a restriction of a smooth function on GN. And in order to check this, I have to check that UN can be given by described inside GL and C by system of equations such that the Jacobian corresponding Jacobian matrix has maximal possible rank. How to do this? So let's look at this formula. It definitely defines UN by a system even of algebraic equations. It involves some complex conjugation, but if you write it in terms of real and imaginary part of the entries, it's perfectly nice. It's just algebraic equations. But the problem is that there are too many equations. You have actually, if you think of this in terms of, if you use this is equation for complex numbers, so you have n squared equations. So the Jacobian of this map. So you can consider GL and C, which is a manifold, and you can consider a map from this group to itself, which takes a matrix A to A transpose, A conjugate, A transpose. So the unitary group is preimage of one of the identity matrix sitting here. We have again a criteria when a level set, when preimage of a point of a smooth map is a smooth submanifold. I recall that this criteria is the following. Geometrically, it means that the differential at every point of this level set, right? So this is pi, and unitary group UN is pi inverse of identity. So in order to check, well, if we could prove that the differential of this map is surjective at any point of UN, we would be done. But unfortunately, this is not true. So indeed, it would be stupid to expect this because these two spaces are the same. So saying that the differential is surjective, the derivative of pi is surjective, is equivalent to saying that it's an isomorphism. But this map has positive dimensional fibers. So there are some tangent vectors which are tangent to UN that go to 0. So this cannot be possibly be the case that the derivative of pi is surjective. So we have to correct it. And in order to correct it, well, we have to use a different approach. And in order to do this, let's modify the target here. So let's look at these matrices. So what happens if I take this matrix and take its conjugate? I take its conjugate and then I transpose it. So then what I get is AT. Okay, so the transposition is anti-involution. So I get the original matrix. So that means that A bar times A T is a Hermitian matrix. So Hermitian matrix is an analog of symmetric matrices for complex entries. So when you take the transpose, you get complex conjugate matrix. So inside this space of all matrices, you have invertible Hermitian matrices. Right? This is here. And this is an open subset in the space of all Hermitian matrices. Right? And what we see is that, so in particular, this is just all Hermitian matrices. This is a real vector space, and this is an open subset. And this map pi actually factors its length here. And now this space has this manifold has smaller dimension. So what you need to check is now that pi, this pi, is has surjective derivative. Okay. So that's the plan. So if we can check that it has surjective derivative, we'll apply the inverse function theorem, and the inverse function theorem will tell us that the level set, namely a pre-image of 1, will be a submanifold, and and then the fact that this UN is a Lie group will become obvious because multiplication is smooth here, and so smooth functions on UN are just distinction of smooth functions on J. Okay, so how to check that it's that this map is has surjective derivative? Let's compute the derivative. So let's compute derivative. Well, and let me do it just at one point, I will take the identity matrix. You can modify this computation easily, or you can argue that it's enough to check using some group structure. You can argue that some group theory, you can argue that it's enough to do it, to check this just at one point. But in fact, it's easy to modify. So let's compute the derivative. So let's see what it means to compute. Okay, so I recall that pi takes a matrix A to A bar times A transpose. I hope I write in this order. Right, yes, very good. So this should be a map from the tangent space at identity to J and C to space of Hermitian matrices, right? Because it's going to be, let me call this space vector space H. So this is a tangent space to an open subset of a vector space. I can identify this tangent space with H itself. So see H okay. Good. So let's compute this. What we are supposed to do. So any tangent vector, this space can be also identified with matrices, right? Because it's an open subset of the group of matrices. Matrices and C. So how this identification works? So if I have a matrix B here, I can look at identity plus C times B and think of this as a path in this group, right? When C is small, it's an invertible matrix, and this is how the identification between matrices and vector space of the tangent space works. So now I take this space and I apply pi to this. So, okay, so let's do this computation. This is going to be identity plus C times B bar plus multiplied by identity plus T B transpose. Okay, so so what this gives me? This gives me identity plus T times B plus B plus B bar plus BT times plus T squared B bar B. Okay, so but now let's remember that I'm interested only in the tangent space. So I'm not, this is a path in H, but it's equivalent to this straight line, right? So now what we conclude from this is that derivative of pi applied to B is just this term, right? B bar.
Excuse me.
dt. Yes.
Excuse me. But
Yes.
if we remove the third term, then the path may go out of Hermitian matrices. So, for example, in this path with T squared is
this cannot happen, and you see, in fact, that so if you
apply transposition, if you transpose this sum and then apply conjugation, then you get the same matrix. This is a Hermitian matrix. This is still an H. Agree?
No, I'm talking about the plus t squared b bt. I mean this matrix, this term.
So sorry, I want to remove this.
Yes, when you remove this, the path, which is the image of pi of t.
This is identity plus this. And
Yes,
both matrices are Hermitian matrices. Agree?
Well, okay.
So that's the formula. So now, in order to check that we have a submanifold, I'm sorry, I don't want to remove it here. So confusing. So this is t squared b bar bt. Okay. So so we get this formula. We describe the differential, and again, our goal is to show that this map is surjective. But that's clear because any Hermitian matrix can be written in this form. So that means that this is surjective. So why any Hermitian matrix can be written in this form? Just if you take a Hermitian matrix A and take for B 1/2 of A conjugate, okay, then this differential applied to this B will be I. So we are done. We computed differential at one point, and we proved that it's indeed well, it's surjective, therefore it's surjective in a neighborhood. So I don't want to invite you to do the computation not only for the identity matrix, but in general, it's very easy. Or you can again say that so this subset of unitary matrices, in fact, it looks the same in the neighborhood of any matrix because there is a left multiplication by an invertible unitary matrix identifies a neighborhood of this unitary matrix inside the space of all unitary matrices with a neighborhood of the identity matrix. And this actually proves that this is a manifold not only in the neighborhood of the identity, but everywhere. So there is a shortcut here. Okay, so that's how you can check that something given by equations is inside group GLN. A subgroup is actually a Lie group. As a matter of fact, there is a well, non-trivial theorem of Lie that asserts that any closed subgroup of GLN is actually a Lie group. Okay, so I still have some time left. So, another example of a Lie group is a subgroup of GLNR. For example, you can take matrices which preserve symmetric bilinear form, OM. So this consists of all matrices with the form, with the property that A transpose times A
is the identity. And very similar computation shows that it's a Lie submanifold here, and therefore a degree. Now I want to go back to the last problem from the seminar list too. So problem it's, let's see the statement. Okay, yeah. So it's problem seminar 2, problem 3. So the purpose of this problem is to show that there are no non-vanishing vector fields on S2. This is a tricky, but so the idea is the following. So we have the tangent bundle to S2. And as we discussed, we have the group of diffeomorphisms of S2, and it acts on everything. It acts here, and it acts here. Inside this group of diffeomorphisms, we have a subgroup, which is S, say, SO 3R, right? So, so what this, so I want to consider the action of SO3R here. So what is TS2? Explicitly, it can be defined, it can be viewed as a subset of PV, where P is in S2 and V is in R3, such that, well, V belongs to the tangent plane, tangent space to the sphere at point P, which means that the dot product of P and V is 0. So it's given by a very simple equation, closed subset here. So, and this space admits a smooth map to R, right? Which takes such a pair, P, comma V, to norm of V, the length of this vector V. So now let's see S2 1 will be the set of all pairs P comma V in TS2 with the property that norm of V is 1. Then, so TS2 minus the 0 section. All right. So if you have a vector bundle, then the base of this vector bundle, it's a space that projects to the base, but also it has a obvious the natural section, the 0 section. So you can always think of your base sitting inside the total space of a vector bundle. So if you remove it, you look at, it means that you look at all such pairs where V is not 0. And you see that this manifold is diffeomorphic to TS21 times times r plus greater, sorry, r greater than 0. The space of all positive real numbers. And the diffeomorphism is very simple. So if you have a pair like this with non-zero v, you just rescale it to make the length equal to 1. So this gives you a map from here to here. The map from here to here is absolute. So the idea, if you want to show that a vector bundle is non-trivial, the general idea is to look at the topological properties of the complement. So if you're familiar a little bit with language of homotopy theory, well, a vector bundle is a map that whose fibers are vector spaces. In particular, it's a deformation retract of S2. It can be contracted to S2, to the zero section. From point of view of homotopy theory, there is no difference between TS2 and S2. In particular, all invariants algebraic topology study, like fundamental group or homology, are going to be the same for these spaces. But when you remove the zero section, when you consider this space, yes, it still maps to S2. But now the fibers are going to be vector spaces minus the origin. Of course, if the vector bundle is trivial, right? If the trivial vector bundle is product of R2 and S2, if you remove the zero section, you just get R2, the R2 minus the origin times S2. It's still not homotopy. It's not. It has kind of different homotopical properties from S2. But it turns out that so you can. So if I will write it down, if TS2 were trivial, then TS2 minus S2 would be homeomorphic or diffeomorphic to S2 times R2 minus 0. That's obvious, because trivial means that TS2 is diffeomorphic to S2 times R2. So you remove zero section, you get this. And kind of a general idea of proving that a vector bundle is non-trivial, again, is remove zero section and check whether this property holds or not. And here you can use invariants coming from algebraic topology, like fundamental group or homology. And many things that we are going to study, like theory of characteristic classes, is a it's a realization of this idea. So we already had the simplest example of the non-trivial rank 1 vector bundle over a circle, whose total space can be thought of as Möbius band. And we observe that if you remove the zero section, you get something connected. Whereas if you take a rank 1 vector bundle, a trivial rank 1 vector bundle, and you remove zero section, you just get R minus 0 times your base, definitely disconnected. So a similar idea works here. So, but in order to realize it, you have to kind of understand this space better, right? So our first step is to use this isomorphism here. The second step is to look at the action of the orthogonal group, SO3, sorry, on this space. Well, it acts on everything, and it definitely preserves tangent vectors with magnitude 1, right? It acts on R3, preserves sphere, so it acts on these pairs. Now, the observation, I explained it last time, that this section is simple and transitive. Meaning that stabilizer of every point is trivial. That's trivial to see geometrically, right? If your element of SO3 preserves, say, the north pole, it means that it's rotation around the axis. So it's if it preserves one vector, it means that it's identity. Okay, so a corollary of this is that this TS to 1 is actually diffeomorphic to SO3. So this kind of discussion of Lie groups was needed to make this statement precise, in the sense that I want really to think of this not just a bijection between sets, but as diffeomorphism. So we already, well, at least this is one of the homework problems to show that this is a submanifold of GL3R, right? And I explained a very similar problem today. So this is a diffeomorphism. Okay. Now, this group is still complicated as a topological space or smooth manifold. So I want to explain. So that's a remarkable result. Proposition that this group, view it as a topological space, as a manifold, is diffeomorphic to real projective space, RP3. So it suggests that given a transformation preserving the Euclidean metric linear transformation of R3, you can construct a line in R4. I don't know of any geometric construction of this. So the argument here is kind of tricky. So what you do, you look at the space of all quaternions, right? So this is algebra. Have quaternions, BI, non-commutative algebra, four-dimensional. So A, B, C, D are your numbers. So it's non-commutative. Square of I, J, and K are squares are equal to -1. Product of I and J is equal to K. J and K is equal to I. And commutator of I and J, I times J is equal to -J times I. Okay. So that's an algebra. Overall. So what are the structures here? So if you have a quaternion, say Z, then you can define its norm to be norm squared is equal to I squared plus B squared plus C squared plus D squared. And a basic property is that if you it's a homomorphism, so it's multiplicative. Okay. So now we are very close to well, at least I can explain the idea of the proof. So let's consider inside the space of quaternions, let's consider subspace, linear subspace H V given by equation which consists of imaginary quaternions. So given by equation A equals 0. So this is just a three-dimensional space. Consider only, you remove this term. So, okay. So now we can consider this vector space equipped with this quadratic form, norm squared. And I consider this vector space with a quadratic form as I have an action of the group of invertible, non-zero quaternions here. So it's just action by conjugation. So if you have an element here called Q, and here you have element Z, then Z goes to U, Z, U equals. It's easy to check that this conjugation preserves imaginary quaternion. One way to see it is the following. So it's definitely this conjugation preserves real quaternions. So where B, C, and D are all equal to 0. It also preserves this quadratic form. Therefore, it preserves the orthogonal complement to this one-dimensional subspace of real quaternions. So it acts here. So this defines a map from invertible group of invertible quaternions. And I recall that quaternions is a skew field, meaning that every non-zero quaternion is invertible to the orthogonal group. So why it defines a map to the orthogonal group preserves this quadratic form, the norm form. It also this group is connected. Therefore, it actually sits here. This is the subgroup of the invertible of the orthogonal group that consists of matrices whose determinant is 1. Well, the determinant is a continuous function, so it must be, and it takes determinant of every element here is either 1 or negative 1. So it's also locally constant. So because this is connected, the image must be in S of 3. Okay. So another property of this construction is that it's definitely if you take for U, if you multiply U by a real quaternion, by an element, by invertible real number, this conjugation real does not remains the same. So it's just because R sits in the center of this algebra. So what you get actually is a map from the quotient of this group by R star. So this is a 4-dimensional space minus the origin, and you mod it out by the action of the multiplicative group. So this is precisely RP3. So that at least gives me a map from RP3 to FO3. And in fact, this map is an isomorphs, which is not very hard to check because the injectivity is in fact immediate because the center of the algebra of quaternions are precisely real quaternions Surjectivity, well, it requires a little bit more work, but you have a theorem of Chalat, which describes the structure of this group. Any element is rotation around an axis, so you can use it to check that this map is surjective. Okay, so let me stop here. So if you have any questions, it's time to ask. And recall that I remind you that next time we meet on Wednesday, not on Tuesday. On Wednesday at 16, 20, 19, 30. Okay. Thank you very much. That's okay.
Thank you.
Thank you.